Okay, everybody, happy Friday to you. Welcome back. Um, I'm glad to be here in person. Thanks for your patience with those 3 days of Zoom lectures and disembodied voices coming from places. I decided upon coming back that I should start wearing an N95 mask. It's too little too late, I think, but it was more to maybe protect others from my breathing or whatnot. But I showed up at my lab research meeting yesterday wearing this, and one of my students says, "What, have you been painting?" And yes, I did get it at Home Depot because I couldn't find it anywhere else. But so it's a pain to wear, but that's what we do. All right, so the exam, which closed yesterday. There are a few students who have yet to take it, so I won't talk about specific questions, items on the exam right now. I will make a detailed video. In the past, I've had like a post-exam review session, but not everybody can come to that, so I'm just going to make a video and post it on YouTube, sort of going through question by question. The average score on the exam was about, I think, a 72. I can't remember whether 72 was average or median. It's one of the others, okay? But there was kind of a broad distribution. So some of you did very well on the exam. Others, I think, are saying that they didn't do as well as they wish they could have done. And so let me provide some context. First question people ask is, how do I know what grade I got on the exam? And the answer is I don't assign grades to exams just at the end of the semester. Okay, well, that's not helpful. So I make you the guarantee that at the end of the semester, it will never be harder to earn an A than getting 93% of the points. Never be harder to earn an A minus than 90% of the points. What that means is if everybody does really, really well on the exam, it's not like at the last minute I say, haha, guess what, 97 is an A. Instead, you have those guarantees. Now, depending on class performance, I can sometimes lower the cutoffs from that. And the way you can tell whether that's likely is sort of by watching the median or 50 percentile score. When that score tends to be around 80%, the cutoffs, especially in the upper half of the class, tend to be exactly what they're listed in the syllabus. However, in the lower half of the class, the cutoffs tend to be substantially lower. So the cutoff between C minus and D is usually way lower than 70%. When the median score on the exam is like 70 or 72, you scale things down accordingly. You're likely not, in the end, I anticipate that the 50th percentile grade, at least historically in this class, tends to be somewhere between a B and a B minus. So that can give you a sense for where you are. But if you want to plan for the worst eventualities, start thinking about the cutoffs as listed in the syllabus. Now, what if you did not do as well as you thought you did? There are two kind of situations you can be in. The first is that you knew you weren't going to do well, and of course, as predicted, you didn't do well. And the second situation is a little more insidious, and that is where you thought you had mastered everything, and yet you didn't. In my experience, students that struggle on this first exam are often approaching the class in, I would say, damage control freshman mode. And what that is you have an insane amount of credits that you're taking. And so the way you manage life is this week, if you've got the physics exam, all you're doing is physics. And then next week you have a paper due in whatever class. And then the week after that, it's OChem test time. Now I'm going to focus on OChem. And you try to pack in a month's worth of preparation in the 24 to 48 hours before the exam. And the reason you're doing this is because it has worked in previous classes. Some of you have taken a lot of general ed classes already, and in a lot of those, if you show up and sort of do the reading, you're already ahead of a lot of your peers, and if you're familiar with the material, you go to take a multiple choice exam and you can eliminate the 2 bogus answers, and then you at least have a 50-50 shot. And so in many cases, simply being familiar with the material gets you an A. In this class, unfortunately, OChem is not like that. Familiarity only gets you to the C level of performance. And the reason for that is that OChem is kind of like athletic performance or musical performance. You would never, before a race or a game, you would never try to condense all your preparation for that into the 24 to 48 hours before. The reason, of course, is that you wouldn't have time to build the skills and the endurance. And instead, you need to spread the preparation out over long periods of time. Similarly, similarly with musical performance, this Christmas I made the mistake of saying that I would play an organ solo in sacrament meeting, and I had this idea of a solo I wanted to do, and it was way outside the range of my ability. But I started practicing early in November, and then life got crazy, and I stopped. I was making time to basically go over to the church every day and play for like a half hour or so, and then I decided I couldn't afford to do that. And so I delayed my preparation, and then it comes to the night before, and I'm frantically trying to get things working, and I have to have my feet moving and the keyboards and the pressing the buttons to change the sounds. And I'm thinking, okay, I need at least another 2 hours of practice on this. And then somebody shows up at the church because they want to practice the organ, so I had to leave. And anyway, by the next day, sacrament meeting, I stand up to go play the organ, and I know it's not really going to go well. I'm praying for God to consecrate my performance to the goodness of my soul, as we're encouraged in Nephi. But the Holy Spirit can't work with nothing, right? So, and so it was a disaster. I mean, I was nervous. I was playing too fast. It was just terrible. But I learned, apparently, a valuable lesson, which is you can do hard things. You just got to give yourself enough time to prepare. So what does studying look like in damage control mode? So first of all, if you're not studying at all, then clearly study. That's the easy thing to do. Some of you are in the situation where you're putting in a lot of time, but you're not seeing the results. And that's possible in musical practice and athletic training as well. And the thing is, you need to improve the study process. So in damage control mode, or even if you're spreading out study over a long period of time, some students look at do a problem in the study guide, and they're in a hurry, so they look at the solution, they see, okay, I missed a few things, but I basically get the gist, I'm familiar with it, I'm moving on. That's like going to the doctor with a complaint, being diagnosed with a specific thing that could be fixed, but not bothering to go pick up the prescription, take the medicine, or do the advice. It's knowing the problem without solving it. So when you get something wrong on a study guide or a practice exam, that is an indicator that you have a misconception, a misunderstanding, a mistake that is correctable, but now you know about it, so you got to do something about it. So you need to keep a running list of things that you're struggling with, and that way you personalize your study where it's going to be most effective. As humans, we love to hear things we already know because it makes us feel good about ourselves. But unfortunately, if you only spend time doing things you already know how to do, there's no growth. And so giving yourself time to make mistakes and correct them is essential to this process. So the good news is, if you're already spending a lot of time, this isn't going to take an additional amount of time, which you don't actually have, but it's being smarter about your studying. You're practicing making time for OChem a little bit every day, 1 to 2 hours every day, and that's going to give you time to see your mistakes and fix them. Once you've identified your mistakes, if you can't fix them on your own, go get help from your TAs or from me. Send me an email with a screenshot of what you're doing. I can often correct misconceptions within just a couple of minutes or a quick email. And let's face it, if you get something wrong on a test, you're going to want to come and talk to me about why you got it wrong anyway. So let's just do that before the test, and then you can get the points, and I can save myself time afterwards, right? Um, so that's my advice to all of you. Now, if you want to talk one-on-one about specific issues, anything I can do to be more helpful, I'm happy to do that. I'll be in my office today. You can stop by. I'm happy to meet via Zoom. If you want to make sure you're going to get me, you can send me an email and suggest a few times, and I will pick one. All right. That was a long soliloquy. 10 minutes of pure talking. Sorry, go ahead.
You were talking about checking where you're at compared to the rest of the class. So we're not able to do that on Learning Suite. Are you going to liberate that so we can see?
Oh yeah, checking where you are relative to the rest of the class. I haven't enabled the stats yet. I never know whether to do that, right? That's a gift and a curse. You kind of want to know, but then you don't. So I will make that available after everybody's taken the exam, which should be in the next couple of days. I'll make it so you can see items missed and what your responses were. Yep. Okay, others? All right. Sorry about that. I feel like that was a dad-like lecture, but I have teenagers, so I'm sort of used to that kind of thing. All right. I'm also used to complaining, so if you want to come to my office and complain, I'm happy to listen to that too. Okay. But let me just say, if you didn't do as well as you wanted to, let's talk. I'll make time to talk to you. Let's see how we can make things better. All right. Now now on to new stuff. We've been talking about enolates and enols, and we had this discussion at the end of class last time about what happens when you go to make an enolate and you have two different kinds of alpha protons that could be removed. And the answer as to what happens is, well, it depends on how you're forming your enolate. So we talked about reversible enolate formation, which is where you're using a base that's not strong enough to completely deprotonate the alpha proton. And you can tell that that's the case simply by comparing the pKa of the conjugate acid of your base with the pKa of the alpha proton. In this case, protons alpha to ketones generally have pKa's around 20. And if we're using a base like hydroxide or alkoxide, the conjugate acid is ethanol, which has a pKa of 16. So that's a 4 orders of magnitude difference, about 10,000 to 1, which means that at equilibrium, in terms of forming the enolate, you're going to have most of your material here, and then maybe less than 0.01% of either enolate. Fortunately, that's enough. 0.01% of a mole of molecules is still a whole lot of molecules. And so that's enough to get some chemistry started. And one of the things we know about Equilibria is if I'm able to shunt off some of this material downstream in a reaction, that's going to pull the equilibrium towards enolate and then to product. When you're in an equilibrating situation, this is general in organic chemistry, when starting materials are in equilibrium with products and multiple kinds of products, the most stable product wins. Do you remember stuff in 351 about, when I go to do alcohol dehydration under acidic conditions, that's in equilibrium, but I form the most stable alkene? The reason you do is because you can go back and forth. When things are in equilibrium, if you imagine a base accidentally removes the proton that leads to the less stable enolate first, well, that's no problem because most of the time it's going back here anyway. And on average, you're going to have more of the more stable intermediate than you will of the less stable intermediate. So why is the purple enolate more stable? We're rationalizing enolate stability based on basically alkene stability. More substituted alkenes are more stable. And that's a principle you learned in 351. If you're interested in knowing more about why, I'm happy to talk about that, and you can come ask me that question. But I think for right now, we'll stick with just that it's true. So the more substituted enolate is more stable. Some of you may have questions about stereochemistry. You'll notice that I've put the alkyl groups trans to each other. There is such a thing as an E enolate versus a Z enolate, and sometimes controlling that stereochemistry is important, but we're not going to worry about it. And I wanted to give you a sort of picture of what we're talking about in terms of an energy diagram. So if we start here in the middle with this ketone compound and our alkoxide base, what we're really saying when we say that there's only that 99% of our material, more than that, is in starting material, is that on our energy landscape, the starting material is a minimum and it's uphill to go either way. And so even the purple enolate, which is the more stable of my two options, that's going to be higher in energy than my starting materials. And that's why I have more of my starting materials than I do of the enolate. So we'll put that up here and we'll just say, I'm not sure how high to put it. We'll just say there's some transition state, and then here is the purple enolate. Then let's have the orange enolate on the other side. And oops, this is a less stable enolate. So what we're going to do is maybe put that there. Don't worry about the heights of the barriers. We haven't talked about what makes enolate formation fast or not, so I'm just going to not attempt to show any difference in the height of the barriers. We'll talk about kinetics later. But here is the orange enolate, which is higher up in energy than here, which is the purple enolate. So you would say that these are high energy intermediates, and of course most of your material is going to be down here at the minimum, but you would have more of the purple enolate than the orange enolate. Is that good? And the reason the energy diagram is this way is because we're using a base that's not very reactive. Okay, so we're not yet going to talk about the reactions of enolates because I want to deal with the second way you can form enolates, which is under irreversible conditions. But just know that we're going to come back and we're going to do things with the enolate. We're going to bring in another reagent at this stage and go downhill to products. So our goal is not to make the enolate, but rather to do something with it. We're not going to get there yet. So stay tuned, okay? Because so far it's like, what is the point? Why would you make 0.01% of an enolate? This, so far, the analogous situation in 351 would be us talking about carbocation stability, right? At any given point, the amount of carbocation is really small. Nevertheless, we talked about it because it influenced the course of the reaction. Same thing here, enolate stability. And just like with carbocations, more substituted enolates are more stable. And knowing that can help you predict the outcome of the reaction. All right, there are two different ways you can do. Oh, wait, any questions you want to ask about that? Yes?
Can that base not act as a nucleophile as well? You said it's not reactive, but...
Could the base act as a nucleophile as well? Sure. So some of you yesterday were mentioning, and I think maybe in the example we did yesterday, there was hydroxide, and we were thinking about hydrate formation. Yes, this negatively charged oxygen could indeed attack the carbonyl carbon. That would get you to, if it attacked the carbonyl carbon, that would get you to a hemiacetal. And that would basically be going from these starting materials in a different energy direction. So I'm not sure how to draw that other than to say this blue line is coming out at you and here's the hemiacetal. Also, there's probably some enols that we haven't shown yet that would be branching off of there. So energy landscapes are multi-dimensional and branching off in multiple directions depending on what happens. And this is definitely the case with carbonyls, where there's a lot of different ways things could go, and which way they go is going to depend on the reaction conditions. We're describing, one of the things we will say is that when we're running this reaction under equilibrating conditions, most of the product is going to come from this low energy, or this lower energy enolate. And we'll use that to explain the products that we get. Is that good? What else? Yeah.
So when you're saying that, the purple is more likely to form, is that because the purple H is more acidic?
That's a good question. So when I say the purple one is more likely to form, does that mean that the purple H is acidic? Yes, in the sense that we've always rationalized acidity by considering the stability of the conjugate base. A more stable conjugate base has a correspondingly more acidic proton. So yeah, you could say that the purple alpha proton is more acidic than the orange one because the conjugate base here is the more stable enolate. Yeah. Is that good? Sort of? Okay, what else? All right, let's talk about irreversible enolate formation. Basically, the principle here is you're going to use a base that is strong enough to completely remove the alpha proton on your carbonyl compound. And that makes it impossible for you to go backwards. So examples of irreversible enolate formation might include this beta diketone, where the proton that's alpha to both carbonyls has a pKa of around 9. And then now imagine using an alkoxide or hydroxide as your base and asking what's the position of this equilibrium. The enolate looks like this, and it's resonance stabilized. We won't draw all the resonance structures, but we could put the negative charge from that alpha carbon onto either of the carbonyl oxygens, and then we would have the conjugate acid of our hydroxide base, which is water. And let's see, we'll draw it like this to remind ourselves that that's the proton we stole from the enolate. The pKa of water is 16. Strongest acid gets to lose its proton. That's, again, looking at that, let's see, 16 minus 9. That's 7 orders of magnitude, 10 million times, roughly. So, 99 point, however many nines gets us to the ratio of 10 million to 1. Who knows? I'm just guessing at this point. Essentially irreversible. Because as soon as you expose that, alpha proton to base, it's getting removed and you're done. Notice that we don't worry about the other alpha protons in this molecule. We only worry about the most reactive one, which is the one in between the two carbonyls. This makes sense thermodynamically too, though, because if we removed these other protons, their pKa's are 20, right? And so it should be way less likely for hydroxide to remove a proton whose pKa is 20 than the proton whose pKa is 9. So what do we mean when things are irreversible? We mean it's downhill. And so this is an example where, because of the stability of the enolate that's formed, because of its resonance stabilization, it's actually downhill to go from the original carbonyl compound and hydroxide to the product. And we're going to use molecules like this a lot in the later part of this chapter to prevent competing reactions when we want to get certain products. The second way you can do irreversible enolate formation is not to have a particularly stable enolate, but rather, wait, I should draw that here, stable enolate, but rather a superreactive base. So we're going to introduce a new reagent. This is a highly reactive but sterically hindered base. So you may remember learning in 351 that the pKa of a proton on ammonia, this is for neutral ammonia going to the negatively charged amide anion, is 38. The problem is that this is, if you take the sodium salt of the amide anion, it's not particularly soluble in organic solvent. But we can make an organic soluble version that has alkyl groups on it, and this is actually even more basic than the amide anion. So this is, diisopropyl amine, and its pKa for this proton is 40. So in order to make this, you'd probably need to use an organolithium reagent as a base that would be strong enough to remove that proton. When we remove that proton, we get 2 lone pairs on the nitrogen with a negative formal charge, and lithium is the counter ion. This is lithium diisopropyl, which is what we call those 2 carbon groups, amide, or LDA. Okay? LDA is a super reactive base. And what that means is if you take just your everyday run-of-the-mill ketone whose alpha proton has a pKa of around 20, and you expose it to this base, LDA. Every time I say LDA, I feel like I'm trying to say El Diablo or something like that. Maybe that helps you remember that LDA is a super reactive base. I don't know. But it should be easy for LDA to remove the alpha proton whose pKa is 20 because, of course, the conjugate acid of LDA has a pKa of 40. So that's 20 orders of magnitude. That's very, very difficult to, I mean, we're going to, do 29s here and just sort of on and on and on. We'll basically call that quantitative yield or quantitative enolate formation, 100%, essentially no ketone left. Yes?
How does terp butoxide compare to pKa?
Good question. How does terp butoxide compare in pKa? The tert butanol, the conjugate acid of tert butoxide, has a pKa, most alcohols it's around 16. For tert butoxide it's around 19. That's the effect of electron donating alkyl groups. So tert butoxide would be enough to get maybe 10% enolate. But if you want 100%, you use LDA. Yeah?
You might have mentioned this already, but what would be the advantage to using LDA over the nitrogen hydrogen, whatever that's called? Right? Because that's what we used to make.
What would be the advantage of using LDA over like this one?
Yeah.
This one isn't particularly soluble in organic solvent, and I think LDA is even more basic. LDA is air sensitive, moisture sensitive, so you have to be careful when you're using it, and so it can be a little bit tricky. You also use it at low temperatures to keep the reaction controlled. But the real advantage to using LDA is what happens when you do reactions under irreversible conditions. So consider a generic energy diagram that looks like this, that could go where you have starting materials here, products that are much lower in energy, product A, and I think I need to make things, sorry, I'm just going to try again. Product A and then product B. A is more stable than B, right? But this energy diagram has our starting materials way high in energy. And let's suppose that both energy gaps here between starting materials and products are so big as to be irreversible, meaning once you go over the hill, there's no coming back, right? In that case, if once you go over the hill, there's no coming back, which is the major product here? B. The system does not care which product is more stable because those two products are not in equilibrium with each other. They're only in equilibrium with each other if they can go back to the starting material and back over the hill. If both products are so low in energy as to not being in equilibrium with each other, stability doesn't matter. Then the only thing that matters is how fast it is to form. Under irreversible conditions, the fastest product to form wins. Okay, so let's fill in let's adjust our Enolate diagram that we drew way back here for the LDA context, right? Copy. Before the two enolates were in equilibrium with each other via this starting material, right? But when we switch the base from the alkoxide to a more reactive base, LDA, suddenly, in terms of energy, I'm going to need way more space for this, so I'm sorry. And this is a crude animation. Suddenly what we're doing is taking the starting materials and moving them up here because LDA is so unstable. And when that changes the energy diagram completely, the purple enolate is still more stable than the orange enolate, but going to the orange enolate is faster. And the reason for this is sterics. Do you see that the orange alpha proton is less sterically hindered than the purple alpha proton? There's just more alkyl groups around it. You see that? And LDA, of course, if you look at it, looks like sterically hindered. It looks sort of, these are isopropyl groups instead of tert-butyl groups. But this sterically hindered base will prefer to make the enolate on the less substituted alpha carbon. So even though the orange enolate is less stable, under these irreversible conditions, this is the major enolate. And again, the reason for that is we're using a highly reactive base, so now our starting materials are way higher in energy than the enolate products. Going to enolate is essentially irreversible, so the fastest product to form wins. Okay? Yes?
And so the less substituted enolate will always be the one that forms fastest.
With LDA, yeah, the less substituted enolate will form fastest. Now, your text uses some language on this for irreversible enolate formation. They call this major enolate the so-called kinetic enolate. All that means is it forms faster. The reason it forms faster is because of sterics. Similarly, your text will talk about enolate formation under reversible conditions. They'll call that the thermodynamic enolate because under reversible conditions, the most stable enolate is the major enolate. So you'll hear the text use a sort of shorthand. thermodynamic enolate versus kinetic enolate. I tend to not do that because I feel like those words can be scary and off-putting to students. So I just go more stable enolate or fastest to form enolate. Yeah.
So I guess kind of going along with that, if you just adjust the temperature of the reaction, can you get more of the more stable? Like if you do a higher temperature, can you get more of the more stable enolate?
Yeah, great question. Thank you. So what is the effect of temperature on a reaction? Temperature generally doesn't change the energy diagram, but temperature, what it is it's kinetic energy of molecules. It's them zipping around in solution. The more kinetic energy molecules have, the easier it is to populate higher areas of the energy diagram. So yes, if you turn up the temperature, you would expect the selectivity between between the more stable, expect selectivity between the fastest to form enolate and the more stable enolate to change. And that's generally true for reactions that are irreversible. If you change the temperature, you're going to change the product ratios. So we'll see your text will use LDA under really cold conditions. You're going to see a lot in the text for enolate formation. Okay, I'm going to take this ketone, I'm going to use LDA, and then it's going to say minus 78 degrees. And you might look at that and say, that is oddly specific. The reason that that's written as minus 78 is that in practice, the way you do this reaction is you create a bath of acetone that you put dry ice in. And the temperature of acetone in dry ice is at some standard temperature and pressure minus 78 C. Whether it's actually 78 C in practice or not doesn't matter. That's code to organic chemists for dry ice and acetone. Though there are more sophisticated like cryo temperature baths that allow you to control the temperature precisely, but this is how people used to do it in the day. So all that means is it's cold. Of course, on an exam, I will probably write the minus 78 just out of habit. Just don't be distracted by it. That means cold. And we're using that to prevent the reaction from being reversible and to make it even less likely for molecules that are in starting material to be able to surmount this hill. Instead, they'll just go over that one. Yeah?
So would we ever see it where we would have this reaction but do it at like 80 degrees Celsius so that we could get the other product?
Would you do this reaction at 80 degrees Celsius so you could get the other product? Sure, but that would be a waste of money. Instead, you should just, if you want the more stable enolate, you should just use hydroxide, which is much cheaper as a base. Yeah, you could, and if you increase the temperature, you can that can cause problems. And so, when people do these reactions, they're very, very careful with the temperature. So, on the other hand, yeah.
So rule of thumb, if it's irreversible, it's going to favor the less stable one, or are there different bases that would?
So that's a good question. If it's irreversible, does it always favor the less stable one? No, stability doesn't matter if it's irreversible. Only it's only about fastest to form. So this is a situation where the fastest to form one is in fact less stable, but it's not a general principle that if you make the reaction irreversible, you always get the less stable product, because irreversible condition stability just doesn't matter anymore. What else? Yes?
So is the transition state for the enolate on the left more stable than the one on the right?
Transition state for the enolate on the left is more stable than the one on the right. Yes, that's why going over it's faster. Yep. Yeah?
Would the hydrogen on the other side of the enolate get taken off too? It's less scared with bigger?
Would the hydrogen on the other side, this one?
No, it's like one.
Oh, you're thinking this one?
Yeah.
That is an interesting thought. The answer is no, because once you are beta to a ketone, the conjugate base would no longer be resonance stabilized. So actually that pKa is right back up to around 50. Yeah. Other questions? Yeah.
Why can't you do a hydride shift?
Why can't you do a hydride shift in the enolate? from like you're thinking, why can't this one move over? Right, so hydride shifts in particular are for carbocations, and the reason they can happen is because a filled carbon-hydrogen sigma bonding orbital, which looks something like this, can line up with an adjacent empty p orbital on the carbon, and literally that hydrogen just leans over with its electrons and makes the new carbocation. So in order for a hydride shift to happen, you have to have an empty orbital that's a place for the hydride to go. In the enolate, the only empty orbital, I guess, would be the pi star, but that's you don't typically see alpha protons move over and attack the pi star. The fact that this is already negatively charged basically means there's no empty orbital over here for this hydrogen to move to. Now, if you're not careful, if you increase the temperature too much, one enolate can deprotonate another. So, and that would be one way to that would be a short circuit path to getting back here. And so we haven't drawn that pathway, but one enolate could deprotonate another ketone, and that could be a pathway to get here. That's why its irreversible formation is so important, because you want to never have starting material again after you've put in the base. Others? No? Yes?
Could you think of an example where in an irreversible process that the least stable, least sterically cured product wouldn't be?
Can I think of a situation where the fastest to form product wouldn't be? Can I ask, let me ask that question in a different way and see whether it's the same question. Could I envision a situation where the fastest to form product would also be the more stable one?
Possibly, yeah. Going off of a previous question about is it always going to form kind of the least substituted, you said no.
Okay. Well, so for enolates, yes. For enolates, yes, the least substituted enolate is always going to be the fastest to form one. There are examples, though, in chemistry where a reaction is irreversible, but you still get the most stable product. The classic example of that was the E2 reaction. I don't know if you remember where a base removes this proton, and you probably talked about situations where you have multiple kinds of beta protons and which is the major product. And we talked about how the more stable alkene is the favored product for an E2 reaction. Sound familiar? But the E2 reaction we run is basically under irreversible conditions. You have this strong base and then this reactive molecule. So if it can't go backwards, then why does it matter that then why do we get the most stable alkene? And the answer we usually rationalize by saying the same things that make the alkene stable must also impact the transition state. So it's not a universal principle that the fastest to form thing has to be the least stable one. It's very context dependent. But with the enolates, in that particular case, yes, the fastest to form one is generally the least stable one. All right. Okay, so let's do some chemistry. I thought we already were. Let's do some reactions. So let's consider the issue of regioselectivity in a reaction called Enolate Alkylation. So you can do Enolate Alkylation by taking a ketone or some carbonyl compound, and you can do this reaction under reversible conditions. I'm using here a base that should not be strong enough to remove a proton. NaOET is just sodium ETO minus ethoxide, which is just this, which is just this. Okay. And then in a second step, remember this is only going to form a very small amount of enolate. Then we bring in some alkyl halide. And that allows us to take the enolate and do the SN2 reaction to make a new carbon-carbon bond. I'm going to highlight that carbon-carbon bond in red between our 3-carbon alkyl halide and then the alpha carbon of our carbonyl compound. So that's why it's enolate alkylation. It's basically SN2 with enolates. There's no issue of regioselectivity here because the 2 alpha protons are similar. This is why you would use the cheapest base possible, because there's no reason why you would use LDA for selectivity's sake. Nevertheless, if you were wanting to waste a lot of money and effort, you could indeed use LDA at -78C. By the way, sometimes your text will put solvent here. THF is a solvent. It's tetrahydrofuran. Its ether solvents are usually good for reagents that have lithium in them. That's neither here nor there, but you might see it. You may wonder about it. So I could, if I want, this would be overkill, but I could definitely do this reaction and get exactly the same product using this approach because both alpha carbons are identical. You might even say that, well, yeah. So now what if both alpha carbons are not identical? What's the situation there? So if we take this ketone, we have 2 different kinds of alpha protons. Maybe for color scheme's sake, I don't know why I've chosen the purple for the more substituted alpha proton and orange for the less substituted one, but we'll just go with it. If you use reversible enolate formation, the major enolate you're going to have is the more substituted, more stable one, not the less stable one. So you're going to alkylate on the purple alpha carbon to give you this product. Okay, and that's simply the SN2 reaction. In contrast, if you ran this reaction under irreversible conditions using LDA at -78C, and then after making 100%, basically 100% of this less substituted enolate, I'm changing which resonance structure of the enolate I drew. That may be troublesome, so I'm going to go back and fix it. And then I add my alkyl halide. It's going to go on the other side. I'm going to get the product, the alkylated product from the less substituted enolate. Okay? And this is an example of regioselectivity. The reversible conditions are regioselective for this product, whereas the irreversible conditions are regioselective for the orange product. These 2 are isomers. If you count them up, count up the atoms, they have the same molecular weight. They are constitutional isomers because they have different connectivity. Another word for that is regioisomers. Selective for one regioisomer over another is called regioselectivity. Go ahead.
How do you keep those reagents from continuing to take off an additional hydrogen?
Great question. How do you get these keep these reagents from taking off an additional hydrogen? With LDA, it's easy. You just use one equivalent of base to make just one enolate, and then you add the alkyl halide. I agree that's a tricky problem for these conditions, and I'm not sure. It's a good question. I think likely what you would do is just use one equivalent of alkyl halide, and after that you don't care. All right, thanks folks. See you Monday.